Okay, all right. Yes, so I'm Per, hi. I'm here with Julian, my colleague. We both work in Pixar's RenderMan team. And yes, there's a very long list of contributors. These are all the people that directly work on the XPU source code. So first, a little bit of background. So RenderMan is Pixar's renderer. It's used for all of Pixar's movies. But in addition, we also sell it as a commercial product. So many studios use RenderMan to do visual effects for their own movies. The first public version was all the way back in 1988. That was even before my time. It's been used to render more than 600 movies so far, still going strong. In the very beginning, or in the early days, it was based on the Ray's scanline rendering algorithm. Over the years, we added ray tracing and many other features. And then later, it became a full path tracer, and that's the version that we call RenderMan RIS. Now for RenderMan XPU. Well, the reason we call it XPU, first of all, is that it renders on CPUs and GPUs, hence XPU. It started as a proof of concept all the way back in 2017, and we've been working on improving it ever since. The goals are mostly three. We want performance, so we want to utilize heterogeneous hardware, CPUs and GPUs. We want a modular architecture, multiple integrators, many different BXDFs, programmable shaders. So that's actually the same as the previous renderer. And we also want versatility. We want a single renderer, both for interactive previews and also to render the final movie frames. And at this point, we finally feel that we're pretty close to having feature parity with the older RenderMan version. So here's an outline of our talk. First, I'll very briefly talk about some related work. Then Julian will come up here and talk about design goals and architecture. And I'll finish that category. And then I'll talk about some results. I'll discuss future work and give a conclusion. Okay, so related work. Let me first talk about GPU renderers. There are several commercial renderers like Arnold, V-Ray, and Redshift that have a separate GPU version. And those GPU versions have somewhat limited features compared to the full renderer. Also, several companies, movie companies, have an in-house renderer. Weta have their Gazebo renderer. At LM, they have Helios Stagecraft. At Pixar, we have one called Real-Time Previewer. Again, because their goal is not to render final frames, that's not really what they do. Then another category is CPU and GPU renderers, like ours. One was NVIDIA's iRay, and that one actually shares the same philosophy as we have, which is that you write the code once, and then you have multiple compilers that target different hardware. Last year, Sony published a very nice paper about their renderer called Spear. So it can render on CPU or the GPU, but not on both at the same time. Then there's Karma XPU from Side Effects. So that one can actually render on CPU or GPU or both at the same time. So that's very interesting, and it's close to our renderer. But they say themselves that it's not a replacement for their fully featured CPU renderer. And then I should also mention Cycles, which is an open source renderer that renders on CPU and GPUs. And here's Julian.
All right, so I'm going to expand on XPU's design goals and describe how its architecture was designed to meet those goals. Supporting heterogeneous hardware not only means high performance on any subset of that hardware, but also means near identical image results, whether rendered on CPU, GPU, or a mix of both simultaneously. To achieve good performance, we prioritize data parallel design throughout. This includes coherent memory access, aligned memory reads to all data, and non-divergent vectorized operations, whether running on the CPU or GPU. XPU also avoids any late binding of dynamic data, which was prevalent and costly in RIS, our previous rendering architecture. In order to ray trace and shade on memory-constrained GPUs, scene load and startup takes place in the CPU, where we can afford to use more memory during the conversion of complex data into smaller GPU-friendly array-based data layouts. And to achieve flexibility needed for production, we settled on an architecture where BXDF, integrator, camera, and display functionality, is added via plugins that are C++ shared libraries, and the rest of it, patterns, sample, and display filters, are written in OSL. So we mentioned versatility for interactive and batch rendering as a goal. These can be at odds. Interactivity also means prioritizing time to first judgment. And that means taking compromises that could result in a slightly less optimal batch renderer. So for example, we use streaming variable bitrate compression techniques during scene load. That could mean less optimal in space, but it's faster to compress. We have to prioritize CPU parallelization during all scene processing stages, and we take care to transfer data asynchronously to the GPU when possible. Prioritizing interactivity also means ensuring that XPU responds quickly to scene edits, but still has a reasonable batch size that takes full advantage of SIMT on the GPU. And then the interaction experience was boosted significantly by integrating the Disney Research Studios interactive denoiser, which works between iterations. For light transport in XPU, we've implemented unidirectional path tracing, although there are no blockers to implementing fancier algorithms such as VCM. We support the usual features such as Russian roulette and depth limits on rays, and also exotic things critical to production. That includes things like LPE-based convergence to speed up rendering of objects under glass. The integrator implements standard next event estimation optimization, also known as direct lighting, with BXDF and light sampling combined using MIS. We use restructured importance sampling as a noise reduction technique for medium numbers of lights, which works very well in the GPU. Physically based light transport is important, but we also need to support bending physics, which is very important for animated films at Pixar. So that means we have to provide light filters, light shadow linking, visibility controls, and trace subsets. Full support for sample and display filters, allow for non-photorealistic rendering techniques, and all of this adds necessary complexity to what would otherwise be a pretty straightforward renderer. So XPU is a wavefront path tracer, which means it's a collection of separate kernels running sequentially on a wave of rays in the scene, rather than a megakernel that processes individual ray paths. This design gives us some advantages. In addition to points raised in the megakernels considered harmful paper, we note that it's easier to stay within cache hierarchies. We can better load balances between cores and multiple devices. And we can, the wavefronts allow sorting of rays and hits between kernels to maximize kernel occupancy. This diagram summarizes the kernels in our system. If you're familiar with the wavefront block diagram from PBRT, this should be pretty familiar. After scene processing on the GPU to organize and upload data amenable for the GPU to achieve vectorization, our rendering code is organized as a collection of kernels that are mostly written only once and compiled for both CPU and GPU. The OSL for shading is just-in-time compiled via the LLVM backend, which can target both GPU and CPU execution. Vectorization for the rest of the code, including the core renderer and the C++ plugins, are handled by compiling with the Intel C++ compiler for SIMD and NVIDIA's CUDA compiler for SIMT. Only in a small number of cases do we specialize some of the kernels for the GPU. For abstracting the heterogeneous rendering devices, we use a virtual device architecture. And so we abstract away details like memory management and the rendering context, which for us loosely means the input buffers needed by the kernel. A key part of this abstraction is the kernel work size, which is 500,000 pixels for the GPU and 1024 pixels for the CPU. And this kind of reflects the nature of SIMT versus SIMD. The GPU number was chosen empirically based on the memory constraints of our current workstation, our lighter workstations at Pixar, and balanced against the ability to quickly cancel renders for artist edits. For task management, kernels are launched by threads onto devices that are mostly run independently based on standard producer worker thread queues. The main synchronization point that we have to worry about are writes to the frame buffer. For ray tracing, XPU is organized using a two-level BVH system. The top level BVH is built over all geometry instances, and the bottom level is a collection of BVHs, one for each geometry prototype. This design, inherited from our previous renderer, allows us to speed up edits. Transform edits rebuild only the top BVH. Deformation edits, or edits to geometry, are localized to rebuilding only a single prototype BVH. Rays fired into the scene are sorted both by spatial location and direction, which helps improve coherency and reduces divergence. And speaking of divergence, on the CPU, unlike the CPU, which uses only one kernel for ray traversal, the GPU not only uses a traversal kernel for each geometry type, we also use separate kernels for geometry that is static versus motion blurred, instance versus non-instance, or opaque versus non-opaque, etc. This is one of our exceptions to write a single kernel for both CPU and GPU. And here we found it necessary to reduce divergence and reduce the register count by doing it this way, and in order to maximize the core occupancy on the GPU. Once we get into a collection of ray hits from ray tracing, these hits are sorted using 3 keys: the geometry type, the pattern network, the material binding, all in order to maximize the batch size of the kernels for shading, since shading for our system broadly involves 3 stages, kernel stages. We interpolate the primvars in the geometry, we run OSL patterns, and we generate and evaluate samples from the BXDF. On the GPU, we use stream compaction to group these ray hits for coherent shading kernel execution, and we launch in separate streams to maximize core usage. We should note here that we don't use optics in our system for reasons why. You can refer to the paper. How we handle geometry and especially tessellation and displacement dictates a lot of the design in XPU. Our approach for subdivision surface meshes is to tessellate fully to micropolygons as early as possible, and then focus in XPU on optimizing micropolygon tracing and shading of micropolygons that don't change over the course of a render or until the next artist edit. This means all tessellation and displacement is entirely complete before any rays are traced. This is a significant departure from our previous renderers, which leverage micropolygon caching. So the processing pipeline for us is a set of irreversible transformations from high-level surface geometry descriptions to micropolygons. And the drawbacks here are that there can be a higher time to first pixel compared to a more dynamic system, and it makes interactivity more difficult as micropolygons may need to be thrown away, and stages of the geometry pipeline may need to be rerun in edits. This pipeline diagram here shows the processing pipeline stages we need to execute or re-execute based on artist input. So the example of the choices in our system: when an artist modifies displacement, we don't retessellate the geometry, but this necessitates that we have to save the fully tessellated undisplaced positions and normals in our system throughout the render. In order to fit large scenes on the GPU, compression of geometry data is extremely important in our system. So we also have to balance compression ratio versus speed because of time to first pixel considerations that I mentioned earlier. Our solution involves, in part, sorting and unifying primvar float buffers using variable bit depth integer indices into these buffers. That gives us about a 3 to 5x compression ratio on geometry with a very small runtime cost when we access that data during shading. All of our 3 float normals are compressed to 4 bytes using octahedral encoding. All data buffers are globally deduplicated. Optimizing the space of our BVHs is also very important. And in XPU, we choose to take a small hit on ray traversal speed. So for example, based on the number of faces in the mesh, we use the smallest possible integer bit depth for face offsets. Bounding box offsets for the nodes, for the child nodes, are often quantized using 1 byte float per dimension. For non-axis aligned oriented bounding boxes that we use for tracing curves, we use an 8-bit quaternion encoding to represent the transform away from axis aligned space for each child node. So this is really important for rendering some of our production scenes. For example, the Coco train station here, which despite the heavy use of instancing, This still requires over 20 gigabytes just for the geometry prototype representation alone in order to represent the 72 million micropolygons. So compression and deduplication gets us down to 6 gigabytes for us. Even with the overhead of the rest of the system, we can easily fit this into a 16 gigabyte GPU, which is typical of our lighters workstations. The hair on Dorothea from Seoul, right on the right side, is an example of BVH compression. The BVH needs 2 million nodes just to deal with 30,000 hairs because of how curly the hair is. And XPU stores it in half the amount of space with the aggressive compression techniques we use. All right, I'll turn it over to Per for the rest of the presentation.
Thank you, Julian. All right, so another interesting aspect is the interactive rendering with XPU. So for example, the camera might move, we might edit the materials, edit the lights, change the texture maps, whatever. And during interactive rendering, it has to be interrupted every time we edit one of those things. And while GPUs are fast, that's great, but they are actually hard to interrupt, especially when we have those large shading groups of 500,000 points. And this can give a lagging user experience. So our workaround for this is to only render on the CPUs in the first few iterations in an interactive setting, and then have the GPU kick in. We also have a progressive pixels mode, so each sample can color blocks up to 16 by 16 pixels initially, and then we go down to 8 by 8, 4 by 4, for a better interactive experience. There's a lot of things that unfortunately we don't have time to talk about here that are in the paper. Subsurface scattering, volume rendering, open shading language. Julian mentioned we use just-in-time compilation, which is great, except when it isn't. We have various materials. Some are simple, complex. The most commonly used one has 10 different lobes and 127 different parameters, so it's quite a beast. We support Material X, and Alain Hostetter from ILM is going to give a talk tomorrow in the hot 3D session. Texture caching and lookups is another interesting aspect. Floating points, different hardware and different compilers have slightly different ideas about floating point operations, so this is something we have to deal with. Our statistics shows the results during rendering, which is a nice feature to have. And now for some results. Most of these are gathered on my computer, which has a CPU with 31 cores, 128 gigabyte memory. It also has an NVIDIA Ampere card with 26 gigabyte memory. And all these images are rendered at 1024 pixels. So here's Woody. On the left, he's rendered with just camera rays, and the speed is 111 million rays per second, which is 9.1 times faster than our old renderer. On the right is ambient occlusion, and there we only care about hit or miss for each ray, so that actually is faster. So here we get 218 million rays per second, which is a 10x speed up compared to the old renderer. Here's some simple scenes. Cornell box, hair to test curves, subsurface scattering, monocloud for volumes. And the speedups here are between 6 times and 18 times. I should point out that the 18 times for the Cornell box is not usual. There's something special about this scene. Maybe it's just that it has very simple geometry or something. Anyways, so we don't always get 18x, unfortunately. Another thing I should mention is that this volume, when we render it on GPUs, it's slower than what we're used to on GPUs. The speedup is only 3.4x, so we still have more work to do. Here are some characters from Toy Story. The speedups here are between 5.3 and 11.3. And here's a more complex production scene. This is Bonnie's room from Toy Story. All the toys, furniture, complex shading, actually very complex shading with many, many nodes in the shading networks. Many textures, 15 light sources, subsurface scattering, 4 bounces of illumination. And I rendered it with 4 64 and 1024 samples per pixel. And the best speed up we get is almost 10x. I also rendered this scene on a big monster machine we have with 192 CPU cores and 2 GPUs. And we measured really good scaling. We're very happy with that. Our friends at our friends at Intel like to point out that if you have this many CPU cores, then CPU rendering is actually faster than GPU rendering. And that's true. It's almost as fast as if you have 2 GPUs. Here's an example of interactive rendering. This is Jesse first removing the camera about a little bit. Then the artist is going to select some nodes in the shading network. So he's selecting the material. The shading network is coming up. It's fairly complex, as you can see. I should mention this is rendering with XPU inside a flow tool, which is an in-house tool. But you can get a similar experience in Maya or Katana or whatever. So here, still selecting material, some parameters coming up. So now he's going to change the material setting. And we'll give it just one more second. There's more of this in the supplemental material if you want to see all of it. But I'll move on. Future work. We should handle many light sources better than we do. So in RenderMan RIS, we have a fairly sophisticated light clustering and selection algorithm. We need something similar in XPU. As far as CPU speedups, well, all of the code is written with vectorization in mind. So we would like to utilize vectorization even more, and also like to use even wider vector instructions, like the 16 wide ones. As far as GPU speedups, as Julian mentioned, currently we do all tessellation and displacement only on CPUs, but why not let the GPUs help out? We'd also like to optimize the volume rendering on GPUs. Another avenue of future work is that currently XPU only runs on Intel and AMD CPUs, and for the GPUs only on NVIDIA, because those have CUDA. We'd like to expand to more platforms. That's one of the main points of having XPU. And we're still currently working on tracking down look diffs between XPU and RIS. There are fewer and fewer, but there are still some remaining, so we still need to work on that. In conclusion, XPU is 2 renderers in one. It's an interactive renderer, and it's also a final frame renderer. It uses heterogeneous hardware for optimal compute power and memory use. It's a big project. It has been and still is a lot of work. And we're happy to see that it's much faster than RenderMan RIS and is very close to reaching feature parity. I should also mention that both RenderMan RIS and XPU are available for free for non-commercial use. You can find it on that website there. I'd like to thank all these great people that we're working with. And that's it. Thank you.
So, yeah, this was an interesting talk and insights into RenderMan XPU. I have one question. Julian, you mentioned that with all the compression, you can get some of the scenes on a 16 gigabyte GPU. Like, what do you think would be like the ideal size for a workstation for an artist and probably also for the render farm? I know everybody would say more is better, but
yes, more is better.
what would be a sweet spot where you would say, okay, we could actually work with that?
Well, NVIDIA will be happy to sell you a 96 gigabyte Blackwell card, but I'm saying that because we actually went to the effort of checking every production shot that Pixar has ever rendered, and they will 99.something% will fit in 96 gigs. So the future is like, yeah, we can do all of our production work on a Blackwell GPU. Now, we're not going to do that right now, but 24, 32 will fit a lot of production scenes, let's say, at Pixar, and where we deal with very, very large scenes.
Okay, but there you're talking about really the complete scene and not just a subset for the artist.
Scene. Yes,
that's interesting. Yep. Cool. Other questions?
Fantastic talk. Can you quickly comment on the load balancing between CPU and GPU if they render on the same frame?
Yeah, they're rendering
It's static or
together.
dynamic, or
Sorry, what was
the load balancing? It's static or
The
dynamic?
load balancing? Yeah, it's dynamic. So, it's assigns there's a task manager that, tries to juggle, okay, the GPU can cover this many pixels and the CPU can cover this many pixels, and then, they will start churning away, and then, results come back, and once a CPU core is done with its job, it gets a new bucket assigned, and the same for the GPU.
So essentially it's atomics of a PCI Express synchronization? So you have an atomic work counter?
Yes, we do. It's an atomic work counter per pixel.
Yeah. Any other questions?
Maybe a follow-up question to that is, those floating point differences that I mentioned is, it's just, when you have floating point operations, the order of, adds actually do matter, and fused multiply adds also matter, and so you can get slightly different results. But that's actually not a new thing, because even on our old renderer that's only renders on CPUs, just switching from one compiler to another, or switching from optimized build to a debug build can actually cause different floating point results. So we're used to that, and we're not aiming for perfection there. We're not saying it has to be absolutely within the last decimal point the same. We can live with differences. We have to live with differences.
Hi, it was an interesting talk. There was a picture you were showing Woody being rendered with ambient occlusion rays.
Yeah.
What was the actual figure? So you were saying that you're getting, RRS was 218 mega rays a second. How complicated is the actual model?
Okay, I skipped that. So it says here 74 subdivision surfaces. They all have displacement. So there's displacement shader running. It also might surprise me, might surprise you. I mean, he's a plastic toy, but he actually has a lot of curves too. It's not his hair. His hair is just plastic, but he has fuzz on his jeans and I think on his shirt also. So just tiny little hair curves.
So in terms of, say, actual triangles, how many are we looking at then?
Roughly, I mean, it's one triangle per pixel, roughly, is what we aim for. Always.
Oh, thanks.
So yeah, I mean, and it's a 1024 by 1024 image. So.
Okay. Then thanks as Peter again. Oh.
Question?
It's just really a minor curiosity that I had since I think Manukas did something similar, like tessellating everything to micropolygons. How do you do that if you don't have at that point the path differentials? Do you have artists that have to bias things if they?
So Manuka went to micropolygons, but they also baked their shading. So that's a very important distinction between us and them. In terms of the size of the micropolygons, is that
Yeah. How do you know when to stop tessellating? Right?
There's a lot of this in the paper, but RIS and RenderMan have always just said, like Per said, the basis, the default metric is the projected size of the micropolygon to 1 pixel.
Yeah, but if you have like a glass lens and everything, right?
Yep.
I'm sure you don't need a differential.
Exactly. Yeah. So we don't. That's not a problem we worry about. And in fact, this is mentioned in the paper, because we're tessellating everything up front. If we are very aggressively under-tessellating things off screen, and so if you have some of a mirror reflecting something off screen, you'll see some facets. And generally, there's a lot of controls that the artists use to dial that under-tessellation back into scope.
Okay, then let's thank the speakers again.
Thank you.